Hello, everyone. Welcome back. Let's go ahead and talk about rate of change problems where we can prove minimum or maximum values. So basically, when it comes to minimums and maximum values, the slope of the tangent would be zero, right? Over here, it looks like slope of the tangent is zero, and here slope of the tangent is also zero, okay? Now, I do want to mention here as well that this method is not necessarily always every time going to give us that, like the method we learned isn't going to give us the exact minimum or maximum every time. It will in the case of quadratics or in any other, symmetrical curve. But in asymmetrical curves, it would just give us the approximate point. There is a method for finding the exact minimum or maximum, no matter what kind of curve it is, but that is a calculus method, so we won't be covering that in this class. This time we're just going to do examples that are quadratics, and so that the ones that are symmetrical, so that we are going to be able to do to find these minimums and maximums with what we have already learned. Okay, but do keep in mind that again, this does just find the approximate ones for other curves that are not necessarily going to give us symmetrical minimums and maximums. And what I mean by that is, this point and this point, they're equally distant, right, from our actual maximum here, our actual local max. But that's not always the case, right? What if we had something like this, right? Something with, a steep slope, and then here we have a less steep slope, right? In this case, is this point and this point, are these points equally distant from the maximum? Well, no, we would end up saying with our method, oh, the maximum is about here. So we still would get approximately the right maximum, even with asymmetrical curves, but not exactly the right place. So I do want to mention that this method just works approximately for non-symmetrical curves. Anyway, we're going to just do symmetrical ones, so it won't matter. So for this example here, it says the height of a glider thrown from the top of a hill is modeled by this function, which is a quadratic, where h of t is the height of the glider and t is the time in the air in seconds. Prove that the height of the glider reached the maximum at t equals 2. Okay, so to do that, we need to find the instantaneous rate of change for t equals 2, and we need to show that that instantaneous rate of change is 0 or approximately 0. Now again, if this was an asymmetrical curve and we were asked to do this, we wouldn't quite get 0 using our approximation method. We'd get something very, very close to 0 though, which would be good enough. But in this case, we will get exactly 0 using the method that we're used to. Okay, so let's do that. The slope of the tangent line is going to be equal to h of 2.1 minus h of 1.9 over 2.1 minus 1.9. And that's going to be, well, let's see, what's h of 2.1? That's equal to negative 5, 2.1 squared plus 20, 2.1 plus 55. Okay. So then we have 2.1 times 2.1 times 5. That's going to give us negative 22.05. Then we have 20 times 2.1, which is 42, plus 55. So that's going to give us 74.95. And then what's h of 1.9? Well, let's see. Let's see what that gives us. That is going to give us negative 5, 1.9 squared plus 20 times 1.9 plus 55, which let's see what that's equal to. 1.9 squared times negative 5. It's going to be negative 18.05 plus, let's see, 20 times 1.9 is 38 plus 55. So let's add all those up, and we get 74.95. So we end up here with 74.95 minus 74.95 over 0.2, which is 0 over 0.2, which is 0. And so because the slope of our tangent line is 0, we can tell that therefore there is a max value here. Okay, so therefore, the glider reaches a maximum height at t is equal to 2. That's where the hand glider reaches that ultimate, that maximum point, because we ended up with 0. Okay, let's move on to example 2. Example 2 says an alligator floating on the surface of water dives towards the bottom of the stream to snatch up food. If the depth of the alligator is represented by the equation h of t equals 2t squared minus 12t plus 13, where h of t is the height of the alligator in meters and t is the time in seconds, prove the height of the alligator reaches a minimum at t equals to 3. Okay, so same thing here, except we need to prove that when t is equal to 3, right, our instantaneous rate of change is 0, right? Because if it's 0, that proves that there is a minimum or maximum there. And in this case, this quadratic, the a value is positive, which means that there is a minimum rather than a maximum. So we already know that there's not a specific maximum other than infinity, right? But there is a minimum. There is a minimum. Okay. All right, so let's get to it. Let's get to it. So for the slope of the tangent line, that's going to be h of 3.1 minus h of 2.9 over 3.1 minus 2.9 to get it to the nearest tenth. Okay, so h of 3.1 is equal to 2 times 3.1 squared minus 12 times 3.1 plus 13, which is equal to, let's see, 3.1 times 3.1 times 2, so 19.22, 37.2 plus 13, which is negative 4.98. Okay. And then we have h of 2.9, which is going to be 2 times 2.9 squared minus 12 times 2.9 plus 13, which that's going to be, let's see, 2.9 squared times 2, that's 16.82, minus 12 times 2.9, so 34.8 plus 13, so 16.82 plus 13 minus 34.8 is negative 4.98. So then we have negative 4.98 minus negative 4.98 over 0.2, which is negative 4.98 plus 4.98 over 0.2, which is 0 over 0.2, which is just 0. So since we've shown our slope is 0, therefore the height of the alligator reaches a minimum at t equals to 3. And there we have it. All right, well, that is it, not just for this lesson, but for this unit. So great work, everyone. And I will see everyone in the next unit. Bye, everyone.